session of today. Oh, hello everyone. I'm happy to open the second session of today. And the first speaker will be Lucio Centrone from University of Bari. Please, Lucio.
Are you able to hear me?
Yes.
Okay. Hi, Ivan.
Hi.
So we can start?
Yes.
Okay. So thank you to the organizers for this invitation and opportunity, as usual. And what I would like to show you today is unfortunately an associative team. This is well, we're gonna talk on this algebras with regular gradings, and well, it's a collection of three works with Plum and Kozlukov, and Kawe Orlando Pereira. He's a very young PhD student and who is facing such an interesting, at least to me, team. That is the one of algebras with such regular gradings. So let me draw you all the path. So we have some motivation and background. I will talk about this in a while. And we have three different parts. The first one is a negative answer to some conjecture by Bakhturin and Regev. The second one is more focused on finite dimensional regular gradings, and the third one is about, of course, the infinite dimensional case. Of course, I will speak about new directions and new results in further directions, but at the very end of my talk. So let us start off with some motivation and background. As I used to say, well, this is, how to say, part of a sort of philosophical path I'm trying to phase out, and is trying to link algebras with non-commutative geometry in a certain sense. But well, of course, let us see what we're. Well, what is non-commutative geometry in few words? Well, it proposes, as I write here, treat non-commutative algebras as a sort of algebra of functions on a certain space. So uh, the idea is the following: several geometric constructions and, or well, first of all, algebraic geometry, of course, depends on commutativity. What I mean? Well, we're simply on a space and two variables are simply commuting each other. And this is the main idea. So what happens to two different variables? They may commute. This is the most important fact in algebraic geometry. But they, of course, can do something different. And for instance, well, if we see in what are the main ideas of algebraic geometry, finding out what differentiation is. So, of course, the key tool in algebraic geometry is finding a sort of differential calculus, of course. Well, yeah, well, I think this, of course, deserves the, how to say, is a starting point for trying to understand, trying to define new geometric structures. Well, as you can see in the first lines of the slides, the drum complex is simply recovered imposing some, well, natural symmetry relations. For instance, of course, you can commute derivation, and you have that derivation of the unit is 0. Well, what happens if we put, instead of commutation, something similar to, what is the first step? First non-trivial step. First non-trivial step is supercommutative algebras. So we have a Z2 graded algebra. I mean, an algebra which decomposes as a direct sum two spaces, two subspaces, and they do behave as well as the product, as the sum, sorry, in Z2. So you have zero component commuting with everybody, and the one component anti-commute with itself. So this is some non-trivial generalization of commutativity. And you have, for instance, a supercommutative word, which is intensively studied for the last 2 decades at least. Well, I decided to put here some observation. Well, ordinary flip, you mean, is replaced by graded twist, reflecting the distinction between, for instance, bosons and fermions. Of course, they are not the only two particles which are called in this talk. Well, and let us read here. Low-dimensional quantum physics are not limited to bosons and fermions. And they have, of course, a mathematical counterpart. New particles appear and a new mathematical object appears too. Well, exchanging of particles such as boson and fermions are more or less, in a certain sense, encoded by a linear operator, satisfying a Young-Baxter equation. So the graded commutativity, which can be the supercommutativity, looks like sort of a spatial case of course, a broader algebraic environment. What I'm speaking right now is, of course, enclosed in a very interesting paper appeared, well, I'm not exactly sure about the date, but at the very early years of 1991. Of course, I'm not that sure, but I'm pretty sure. This paper is a paper by Bayes, appeared in Advances in Mathematics. Well, so let us start off with the core of this background and motivation of my work. So our algebra is an associative algebra with, of course, a Young-Baxter operator with the sort of compatibility multiplication. In few words, you can see here. Well, I'm trying to indicate this. Well, the multiplication is invariant under such an operator. Okay? So, in few words, you have something like, we have two variables, x and y, and what happens to x and y if their product xy depends on yx under some operators? And this is the idea. So let us go into the explication. This is more story about. Let's go through. I would like to speak about polynomial identities at the moment. So F is a field, X is a countable set of non-commutative indeterminates. You take the algebra of polynomials, the free associative algebra, freely generated by the set X over the field F. So we have the common notations, and we, of course, we shall call polynomial each element in this algebra. We say, if we choose an algebra, we say that a polynomial is a polynomial identity if it vanishes under substitution of every element of the algebra A. This is a very important stuff. Core is the set of polynomial identities of a given algebra. Okay, we shall denote it by int E, and it is invariant on all endomorphisms of the free algebra. It is also called a T-ideal. Of course, if we have a set, we have the smallest ideal, T-ideal, containing S. And this is called the T-ideal generated by S. And last but not least, the set which has an algebra structure called free of A, which is the relatively free algebra of A. Examples of polynomial identities are commutative algebras, or finite dimensional algebras, or the Grassmann algebra. All of these are examples of polynomial identities. Okay, we have a PA algebra over a field F. I would like to show you one of the more principal characters of the theory. So you consider the space of multilinear polynomials and you quotient it by the identities of A. Well, it is an Sn module and it is also a vector space. So it deserves a dimension called Cn of A. And if you consider this limit when it exists, this is called the exponent or pi exponent of the algebra A. In few words, we need such an exponent to measure the rate of growth of polynomial identities. In the associative case, characteristic 0 is always a non-negative integer. It is a well-known result by John Bruno and Misha Zaitsev. And it is chi-square, for instance, for matrix algebras. I already told you what a Z2 grading is, but now we take a general group, a Abelian group. We decompose A through the element of G in subspaces, but it should have one more property. The component may behave as a group. This is what we call a G-graded algebra. And now let us define what a regular grading is. Well, the G grading is regular, in few words, if it has no monomial identities. This is encoded in the first part of the definition. And the second one is strictly linked to my large introduction. Look at this. We have two elements of the group and two homogeneous elements. I mean, elements belonging to such subspaces in which we decompose the algebra. And they do not commute, but they are close to be commutative. There's some map here going from G to K star. It is also the map is a bicharacter of the group G. We also have a matrix we can build up looking into the entries of such map beta. Well, the G grading is called minimal if the decomposition matrix has no repeated columns. For instance, this one is not minimal, but of course it relates to a commutative algebra. Because you see, this beta GH here, if they are one, the homogeneous component do commute each other. Let us show some example. Infinite dimensional Grassmann algebra E. It's simply a quotient of the free associative algebra by the ideal generated by xi xj plus xj xi. Well, it has a natural Z2 grading, which E0 is the span of even length monomials, E1 is not. And what we have here, as I told you at the very beginning, the zero part commutes with everybody, but the one part anti-commute to itself. So it is a minimal grading, no repeated columns. M and F full matrix algebra take a primitive root of the unity, and we have such grading defined by this guy. The bicharacter here is given by this expression in terms of zeta. And well, the determinant here is depending on n to the n squared. Well, I cannot show you up the matrix, the full matrix, but in characteristic 0 is always minimal. One more example, this Q-group algebra. So we take a cycle, a finite abelian group, and of course, we have such information about element of the basis. In this case, we say that the group algebra as a trivial or a natural structure of a regular G grading. So, what is the first thing we have to phase out today? Negative answer to a Bakhturian-Regev conjecture in positive characteristic. So, let us see what is the Bakhturian-Regev in characteristic 0. The regular G grading is minimal on an algebra A if and only if its determinant, the determinant of its matrix is not 0. Aljadev and David showed a Bakhturian-Regev conjecture over 0 characteristic fields. It's always true. And they also gave us a very interesting shape of the determinant of MA. More precisely, they show the regular grading is minimal if and only if its decomposition matrix has a non-zero determinant, and the determinant is the following. Moreover, we have a very, very interesting link with PI theory. The exponent of the minimal grading of the algebra A as an algebra equals the cardinality of the group G. What happens in positive characteristics? you choose a prime P and a conjecture fails. For instance, you consider G being the usual direct product Zn, and consider the relatively free algebra generated by such polynomials, and C as a minimal regular G grading, but its determinant is 0. Let us show off an interesting relation between cocycle the cocycle defining as Q group algebra and minimality. The key rule is played by G0 alpha. If G is any group, we define this G0 alpha being the set of elements so that alpha GH equals alpha HG. And this gives us the possibility to construct a wider class of counterexamples. Again, take an infinite field of characteristic P, and we choose ZP times ZP times ZP. Well, in this case, we show there exists alpha having the cocycle structures so that Q0 is not 0 and not Q. It is possible to consider the associated bicharacter associated to alpha, take the quotient, and we prove there exists delta so that A F delta G, this Q group algebra F delta G is G regular, minimal decomposition having beta as its bicharacter. And the determinant of MA is 0 because P divides the cardinality of G, and the determinant looks like the product of the order of G times something. What about finite dimensional regular gradings? Well, first step, what happens if you have a semi-simple finite dimensional algebra? First thing is studying the behavior of its Jacobson radical. We found out if you have a minimal degrading, this minimal degrading goes through the semi-simple algebra A over JA. We can say a bit more. They have the same bicharacter. What does it mean? It means we can study graded simple algebra if we want to have a complete framework. And in this case, of course, saying an algebra G-graded and G-regular means something very strong. And this is the result. Finite dimensional graded simple algebra having a regular G-grading and full support. For full support, I simply mean if we choose any of the elements of the group, say G, the component AG is not 0. And the result is that the dimension of each homogeneous component is 1. And as a graded algebra, A is isomorphic to a twist group algebra for a suitable cocycle. alpha. So imposing such a kind of hypothesis on a graded simple algebra means giving out a skew group algebra. We have something more. We introduced the so-called complete support. What is a complete support? In few words, you simply have to admit that the semi-simple part of a finite dimensional G algebra is isomorphic to a skew group algebra. In this case, the question leads to the following result. So assume a complete support on a finite dimensional G-graded algebra with a regular grading. Suppose the Jacobson radical of the zero part of A is not zero. Then we can find out a commutative algebra in which these conditions are satisfied. So A turns out to be a skew group algebra, tensor, such a commutative algebra. And if P is the maximum semi-simple subalgebra of A, so that A0 can be decomposed by this P and its Jacobson radical, and supposing the dimension of P is 1 and the Jacobson radical is 0, this of course gives us the previous result. And the connection with PI algebras. Finite dimensional algebra with minimal regular grading and complete support. And also in this case, the graded PI exponent of A coincides with the ordinary PI exponent. Well, if we compare the version by Aljadev and David, they make a very strong sentence comparing showing off the exponent of A is exactly the order of the group G. In this result, I would like to point out, here we say the PI exponent coincide with the graded PI exponents, which is a sort of a weaker definition of the exponent of A, taking in consideration not only ordinary identities, but graded identities, which are identities with a labeling given by the elements of the group. And of course, this is a weaker condition and a weaker definition, right? Well, simply resume. What can we say from the point of view of geometry in a certain sense? This regularity controls commutation. The fact we have a minimal grading, we are simply canceling out some symmetries, and we simply have a twisted group algebra. Okay? So here the ideas is trying to develop the geometry by bias in some concrete algebraic environment. And this, in few words, simply means what is this shows you what is the focus of our work. Trying to understand in the language of bias what are the concrete algebras in which we can work in order to define new and concrete differential calculus in geometry. And in the finite dimensional case, we have a very interesting and complete answer. Well, we simply need to explore a bit more infinite dimensional regular case. And in our work, we decided to work only on Z2 graded regular algebras, having minimal decomposition. And I would like to directly show you off the main result. Again, we are an associative word. We have a unital algebra, algebraically closed field of characteristic 0, regular Z2 grading, and regular decomposition minimal. Well, this is almost surprising, but the associative by character is uniquely determined, and it coincides with the one I showed you of from the Z2 natural grading of the infinite dimensional Grassmann algebra E. Well, this says a bit more. This says the Grassmann algebra E is always embedded in a Z2 graded regular algebra. And this leads to the conclusion that each minimal Z2 graded regular algebra has an infinite dimension. It appears inside the algebra. Well, in few words, what happens here, just to depict a bit the situation of the proof. We decided to work on a weaker definition of regular algebra. And we say an algebra is n-regular if it does not monomials of degree n as monomial identities, but it admits identities of degree greater than. In each of these cases, we can find inside the algebra, inside the decomposition, a copy of an n-dimensional Grassmann algebra. And we worked with a direct limit of such an algebra, and we've simply found out the Grassmann algebra E is inside the original algebra. So it's simply a work using direct limit technique, but something easy to be handled. Well, moreover, such algebras, I mean, Z2 graded and regular, are exactly those algebras having such the so-called Grassmann envelope, which comes out from a finite dimensional graded algebra, which is commutative and also regular. Let me explain a bit more. I would not like to, well, I decided to don't carry on with technicality. But the Grassmann envelope of an algebra, of a Z2 graded algebra, is the following. Suppose A is Z2 graded, so you can imagine A decomposing as A0, direct sum A1. And if you consider a Grassmann algebra, the infinite dimensional Grassmann algebra E0 sum E1, you have that the Grassmann envelope of A is the direct sum of E0 times A0 and E1 times A1. This is the Grassmann envelope. And what we showed off with our in our paper is exactly what I wrote at the bottom of this page. Their algebra, the Z2 graded regular algebras, are so that the Grassmann envelope of such an algebra is exactly the Grassmann envelope of a commutative and regular algebra. Of course, the structure is really complicated, but of course, I would like to show you something which is understandable from a large public. Would not like to lose myself in, well, in explication which are not that interesting to be showed off. And well, finally, I would like to say something about finitely generated graded subalgebras. Well, we show there the structure of such algebra can be described once again, in terms of Grassmann algebras, commutative components. And as I told you before, we gave a very specific description of the building blocks of such algebras. Well, what is the problem here? If you try to imagine a G-regular algebra, Z2 graded, and you imagine the Grassmann algebra inside this algebra A, the problem is the existence of Z2 graded elements of degree 0 annihilating the Grassmann algebra. And the structure of such elements repeats infinitely. And what is the problem? The problem is that such elements cannot be controlled by a simple direct limit. There's something which is left still. So we have not a complete classification, but we have in the case of finitely generated algebras. Well, we also I would like to, is my time over? Is my time over? Well, so let me just, if my time is over, I would like to show you how simply
Don't worry, you have 20 minutes.
Okay. I'm close to the very end of the talk, and I'll try to speak just a bit faster. And what happens if a G-graded algebra has the same graded identities of a regular one? And we gave this result. Z2 graded algebra satisfying the same graded polynomial identities of Grassmann algebra E, then A is Z2 graded regular and has a minimal regular decomposition. So this is a sort of classification theorem. And at the very end, consider a Z2 graded regular algebra with minimal regular decomposition, and every finitely generated graded subalgebra of A admits a structural decomposition involving finite Grassmann algebras and commutative components. This is what I tried to explain to you some minutes ago. And this is the very end of my talk, but I would like to point out some new direction. My talk, of course, is over, but I would like to spend some word about the new direction of our research. First of all, as maybe you noticed, well, such a theory, at least what we have done with Plamen and Kawé, are related to an abelian, finite abelian group. What happens if the group is not abelian? Of course, that the same definition works for finite abelian group in general. Well, what it doesn't work is a possible generalization or regularity to H-module algebras, where H is a Hopf algebra. And this is what, our next step. Generalizing such kind of structures in order to go a bit more in details in a quantum group environment. Well, the main problem is trying to attach the two definitions. The first about monomial non-identities, and the second one is the definition regarding concerning the commutation of homogeneous elements. They must have a counterpart in H-module algebras. But if you try to generalize one of them, you lose information somehow for abelian groups and in some other sense for non-abelian groups. So we are trying to balancing everything in order to go a bit more faster in this how to say research environment. But I mean the path is still too hard to be phased out, and now I'm really finished and really over.
Okay, thank you for your talk. Some questions, comments, please. No questions? Okay, no questions, no problems. And we have break, 15 minutes. Okay.
Okay, thank you, Ivan, and thank you once again for the opportunity, Ivan. I hope to see you as soon as possible.
Yes, very soon, very soon.
Very soon. So let us see later for a new talk. See you. Thank you so much.